Here we finally get to use MATLAB to find numerical solutions to these ordinary differential equations that we've been playing with and have put into state space form. So in this case, we're going to pick up where we left off with a previous example. We put our ordinary differential equation into state space form. We defined x1 and we defined x2. So remember from the previous example, x1 was equal just to x, and x2 was equal to x dot. So what we're going to be solving for is x and x dot between 0 seconds and 15 seconds. And we're also given the initial conditions, which we'll get to in a minute here. So before we can solve it, I need to make a new M file that its only job is to assemble x dot, or the derivatives of my state variables. So I have to define a function with one output to use this, the output being xd, which is what I'm going to call x dot, and that's just going to be a column vector of x1 dot, x2 dot, and I'm going to call this ODE for ex1. As my inputs, I have to use the independent variable t, or time, and then my state variables, which is going to be x in this case. So x is a vector of my state variables, in this example x1, x2. So first, we do always want to pre-allocate the size of xd, or x dot. To use ODE45, x dot must be a column vector. So I'm just going to make it zeros for the moment. That way it's a vertical column vector, so it's a 0 on top of a 0. Then I can fill in what the values actually should be. So based on the equations I wrote previously, x1 dot, which I'm going to write as xd of 1, we know its right-hand side is just x2. And in MATLAB, that's going to be x of 2. So all this does is define what is x dot, x1 dot, and it's x2. I then need a definition for x2 dot. Again, from my state variable equations, I know that's negative 7 over 4 times x of 1 plus 1/2 times x of 2 plus 3 over 4 times sine of t. Right, so again, what have I done? I've pre-allocated that it's going to be a 2-element column vector. I know there's 2 elements to it because I have as many elements as I have state variables, because this is defining the derivatives of each of my state variables. I pre-allocated it, then I define x1 dot according to my equations is just x2, and then x2 dot is negative 7/4 x1 plus 1/2 x2 plus 3/4 sine of t. So I'm done for the moment with this. Again, this M file just creates the x dot. Now I go back to my main M file so that I can actually run it. Right, so my outputs, I'm going to get timestamps. I'm going to get the values of the state vector x. Remember, the first column of x will give me the values of x1. The second column will give me the values in x2. So to call this, I'm going to use ODE45 at tx, and then the name of that M file I just made, ODE4ex1. And that took only 2 variables, t and x. I do have the options here to add other arguments that can take, so I could put an a in here, and then over here I could say this is a times x of 2, and that would be okay. The way I suggest using this is always have the first one be your independent variable, the second argument be your vector of dependent variables, and then put any extra ones that you want. In this example, we don't need any extra ones. So that is where, if there were extra ones, we could pass the value. So if we wanted that a to be 5, I could put 5 in there. But in this case, I don't need that. Alright, so again, that first argument is the at tells it which values ODE45 is going to be operating on. It always expects the first one to be your independent variable. It always expects the second one to be your vector of dependent variables. Then the function that contains really the state space relationship. Then the second argument is going to be the time span. Here I want to simulate this for 15 seconds. So I want to start at 0 and run it until 15. And I'll put a comma between them. The third set of values is my initial conditions. So in this case, I'm using initial conditions of y of 0 is negative 2. So remember, y of 0, or y mapped to x1. And y dot of 0 is 4. Y dot mapped to x2. So this is saying that initially x1 of 0 is negative 2, x2 of 0 is 4. And then I close it out. Right, so the function I want that contains my state space variables, the time span I want to run it for, and then the initial conditions on the state variables, everything in that same order. So if I run this, right, one more time, we see in the workspace I have t and I have x. If I just look at them quickly, t is, again, the timestamps that it's solved at. By default, it makes a decision where in between 0 and 15 it's going to have solutions. And if I see x, x contains, the first column is x1, which is my values of y, and the second column is x2, which is my values of y dot. So I am often interested in here is I want to plot probably the timestamps versus the first column of x, because the first column of x is x1. In this case, that's just y. Okay, so here, what it's plotted is the value of y from 0 to 15 seconds. So this is the value of y that satisfies that original ordinary differential equation that I came up with. So if I add labels to this, that's going to be time as my x-axis, and y is my y-axis. And if I wanted to, I can also include, I'll make it a subplot here. Not only do I want to look at the values of y, but I can look at its derivative as well. So that's going to be the second column of what I'm calling x, because that's x2, which is x dot. So this is dy dt. So making this a little bit bigger, the top plot here is y versus time, and then I have dy dt, or y dot versus time. This lower graph is just the derivative of the top graph. So to recap, I now have values for y, I have values for y dot from 0 to 15 seconds. However, I don't have that closed form solution that gives me what is y at every value of t. I really only have values of y at specific values of t. Again, these specific values of t. However, if I do want to know what's happening in between, at this point I could use an interpolation between the values that I didn't have originally. Or if I do want it at more values than just the t it came up with, I can modify how I put in these start point and end point. I just said start at 0, go to 15, make your own decision of what to do in between. I can specify by putting an actual vector in here. So here it's going to solve it every 10th of a second until we have 15 seconds elapsed. So if I rerun it now, and now I look at t, it solved it at specific places in time, again, every 10th of a second. And if I want an even finer grain solution here, I can keep doing that, and it's going to solve it at these specific locations. Now again, if I want to know at 5.1794 seconds what happened, I'd still probably want to use some sort of interpolation between these values to get the value of y or dy dt at that time.